Glass transition temperature. A particular temperature above which polymer act as soft, flexible and rubbery in nature, and below which the polymer act as hard, brittle and glassy, is known as glass transition temperature Tg. So glass transition temperature is the temperature above which a polymer acts as soft, flexible and rubbery. And the same way, flow temperature is the temperature at which polymer melt. So temperature at which polymer melts is known as flow temperature TF. And the glass transition temperature is mainly depends on the segmental motion or molecular motion of the polymer. And the segmental movement or molecular movement is mainly depend on the factors size, then flexibility of polymer, then third one molecular aggregations, then the fourth one geometry. In addition to segmental movement, glass transition temperature also depends the factor molecular weight of the polymer. So first one, segmental motion or molecular motion. Segmental motion decides whether the polymer exists in solid state or molten state or in rubbery state. If the segments are moving very freely, then we can say it is in molten state. If segmental motion is restricted or the segments are fixed, then we can call it as a solid state polymer. Or if segmental motion is in between the molten state and the solid state, it acts as a rubbery substance. So segmental motion or segmental movement is the main factor which decides the glass transition temperature. And the factors which influence segmental movement, the first one is size. We can relate the size of molecules with molecular weight of the polymer. And we will discuss about it later in this video. Okay. First of all, we are going to discuss how flexibility determines glass transition temperature. So flexibility determined by the degree of freedom with which the segments of the polymer along with the backbones can rotate around the covalent bonds. So flexibility is determined by the degree of freedom with which the segments along with the polymer molecule can rotate around the covalent bonds. If the polymer chain is linear, then it is easy to rotate. That is, degree of freedom is very high. High degree of freedom. But if bulky groups are there as branches, that is, if the polymer is highly branched, then it is difficult to rotate. So, degree of freedom is less degree of freedom. That means if the polymer is linear, high degree of freedom, and hence the glass transition temperature is very less. On the other hand, if the polymer is highly branched, then degree of freedom is very less, and hence glass transition temperature is high. And the flexibility can also express in terms of the intermolecular forces exist between the polymer segments. Intermolecular forces. If the intermolecular forces are weak, such as if the intermolecular forces are van der Waals type bonds, then it is highly flexible. Or if intermolecular forces are little bit stronger than this van der Waals forces, that is if dipole interactions and hydrogen bondings are there in polymer molecule, then it will become less flexible. So it becomes more crystalline. So it becomes more crystalline when dipole interactions and hydrogen bondings are there in polymer molecule. So we can say the hindrance to segmental rotation and the forces between the polymer molecule restrict the free movement of segments. And hence solid nature increases or glassy nature increases and the rubbery nature decreases. And hence glass transition temperature increases. Now we have to know the reason behind this, right? So actually there are some intermolecular cohesive forces exist in the polymer molecule. So intermolecular cohesive forces are there in polymer molecule. At the same time, the thermal energy of polymer molecules leads to the thermal vibrations of the polymer elements. So thermal energy of polymers leads to thermal vibrations of the polymer elements. So when the thermal energy exceeds, when this exceeds the intermolecular cohesive forces, the segments of the polymer are started to move, or it converts to a rubbery state. So naturally, the thermal energy of polymer is difficult to exceed the intermolecular cohesive force. So when we increase the temperature helps to increase the thermal vibrations of the polymer molecule and it exceeds the intermolecular cohesive force. And that particular temperature is what known as glass transition temperature. So that means when the polymer is less flexible or when the degree of freedom of the polymer is less, then we have to give more amount of thermal energy to exceed the intermolecular cohesive force. That is why glass transition temperature increases when flexibility decreases. Already told that bulky side groups bulky groups increase glass transition temperature. For example, if aromatic side groups are there, that increases glass transition temperature. For example, the glass transition temperature of polyvinyl carbazole is about 150 degree. Polyvinyl carbazole actually contain a side group like this, an aromatic side chain. So this aromatic group increases the glass transition temperature of polyvinyl carbazole. So this is the basic structure of polyvinyl carbazole. Enzymes. Here the presence of the aromatic group in the polymer chain increases the bulkiness of the polymer and hence the segmental movement reduces. So the glass transition temperature increases to a value 150 degrees Celsius. Same way, the aromatic ring in the basic skeleton is also increases glass transition temperature. For example, polyethylene terephthalate So here in polyethylene terephthalate, the basic skeleton containing an aromatic ring. The remaining part is like this. Same way here also. Enzymes. Here the aromatic ring is in the basic skeleton, and the presence of this aromatic group also increases the glass transition temperature. So we can say any stiffness in the polymer molecule leads to the increase of glass transition temperature. So an important example is ladder polymer. The name is coming from the similarity of this polymer with ladder structure. So the polymer structure is this. So the structure will be repeated like this. And this is the basic structure of ladder polymer. Here also glass transition temperature is very high because of the stiffness. Then if you talk about the geometry of polymers and its relation with the glass transition temperature, some of the polymers possess a regular chain backbone and these type of polymers are crystalline in nature. That means we have to provide more amount of thermal energy to convert it into a rubbery state. That means glass transition temperature is high. Okay. Then there are some particular type of polymers which are irregular in nature. So these irregular polymers itself exist as rubbery substances or they are or we can say their crystallinity is very less or less crystalline. Hence, the glass transition temperature of these substances are very less. Similarly, we can say if polymers are stereoregular, then they exist as crystalline polymers, or we can say their crystallinity is more, and hence glass transition temperature is also very high. On the other hand, if they are not stereoregular structures, then their glass transition temperature is very less. Same as that of this, we can relate the glass transition temperature with symmetry also. That means if the polymer is more symmetric, then it exists as crystalline substance and the glass transition temperature is very high. This is about the geometry of polymers and its relation with glass transition temperature. Then the next factor is molecular weight. That is how molecular weight of polymers relate with the glass transition temperature. So actually, glass transition temperature is directly proportional to molecular weight. When molecular mass increases, glass transition temperature also increases. And we can draw the graph like this. Here y-axis, glass transition temperature is in y-axis and molecular weight in x-axis. Particularly, we are mentioning the number molecular mass of the polymer. So, the graph will be appear like this. First of all, it increases steeply and then becomes steady. So, this means actually this relation is only applicable to the molecular weight up to 20,000. So, this is, we can relate molecular mass and glass transition temperature of polymers up to molecular weight 20,000. So here molecular weight is around 20,000. And there are two important mathematical relations which relate glass transition temperature and number average molecular mass. One is Tg equal to Tg infinity minus K divided by Mn dash. Here Tg is the glass transition temperature and Tg infinity is the glass transition temperature at infinite molecular mass. And Mn is the number average molecular mass and K is a constant. And this equation can also represented like this by taking the reciprocals, that is 1 by Tg equal to 1 by Tg infinity plus A by Mn dash. Here A is also a constant. So these are the two relations which express the dependence of molecular weight on glass transition temperature. Then we have to familiarize one more word along with glass transition temperature, that is plasticizers. So plasticizers are the substances which helps to reduce the glass transition temperature. So this substances reduce glass transition temperature. How? Actually, plasticizers are low molecular weight substances, low molecular weight non-volatile substances. So when we add plasticizers into polymer, these plasticizers penetrate into the polymer matrix and establish bonds with the and establish bonds with polymer elements. So naturally what happens is already existing cohesive forces are reduced by this interaction. So cohesive force, already existing cohesive force reduces. So what happens? The segmental moments increases and hence glass transition temperature reduces. So this is what happens when we add plasticizers into polymers. So many plasticizers are there. Some examples are, one is dibutyl phthalate, and the next one is diisooctyl phthalate, diisooctyl phthalate, etc. And the extent of reduction of glass transition temperature is different for different plasticizers, and it is known as plasticizer's efficiency. So plasticizer's efficiency is the extent of reduction of glass transition temperature by different plasticizers.
So this is all about glass transition temperature.